Welcome back. So let's continue with our improper integrals. So in this video we're gonna talk about improper integrals, and the improper integrals is when one or both boundaries approach infinity. So what do I mean by that? If I have a function dy dx and I say that it's just x, right? Then your graph would be the following. So your x would be here, and then your dy dx would be here. This would be your range. And then if it equals x, then you just have a straight line, right? And now let's say that you want to calculate the area under the line starting from x equals 0 up until when x approaches infinity. And remember, here x does not equal infinity. It approaches infinity, alright? So it's a different concept. It approaches infinity. It cannot equal infinity, but it can approach it. It can get larger and larger. X approaching infinity essentially means that your x gets larger and larger. And then if you take the integral of this function, then you get the area under the curve. And intuitively thinking, what would be the answer? Well, it should probably be infinity, right? Because if you think about it, then as your x approaches infinity, then well, here your area gets bigger and bigger, and also your accumulated area, this continuous recording starting from the beginning, gets bigger and bigger. So obviously if x approaches infinity, then this area here will get bigger and bigger, and it will also approach infinity. Now, how would we formulate that mathematically though? So mathematically we would formulate it like this. We would have dy equals x dx. Then we would put our integral signs here. We would put zeros and zeros here, and then here we would put x and x, so it's just a variable. And then we would put a limit here, limit as x approaches infinity, and here as well, limit as x approaches infinity. And then you would simply calculate the integral. So it would be the following. It would be y equals limit as x approaches infinity. And now you already know that the answer would be 1/2. Then here you would have x squared. And then you would go from 0 to x, and x approaches infinity. So your y would be then 1/2, and then here you would have x squared minus 0. But then you should not forget that you have to put limit here as x approaches infinity. And if you do that, then here this x gets bigger and bigger, so your y in the end will approach infinity. Okay, it's logical, right? It's logical. Because essentially, if you think about it again, that integrals are area under the curve. That's one way of looking at it. But then the other way of looking at it is that you're continuously measuring the area, in this case under the line, you're continuously measuring the area from the start. And then integral means that you take this area that you're continuously measuring, right? You still have the same input, x, but now you have a different output y, and your output y is continuously measuring your area. So this area that you have here under the line, you now make a range out of it, right? So if first you have this kind of function, your x is your input, and then your f1 as a function of x, and then you get dy and dx. Then if you take the integral of it, then you still have the same input, x, right? You still have the same input, but now you have a different function, f2 as a function of x. So f1 as a function of x here was just x, but then f2 as a function of x now here would be 1/2 x squared, right? So this would be your function here, and then your output here would be different. It would be y, and this y, it's your area under the line, and as you go along x, then you always measure how much area you have already covered starting from the beginning. And for us now the beginning is 0. So you now take this area and you say that, okay, my area is now represented on this number line, on this output number line, and then you get your parabola here, and your parabola here, well, you get this function, and this function is a parabola like this, and it's logical that if your x goes to infinity, then your y, or your accumulated area, your area under the line, also goes to infinity, right? So that's why you have your infinity here. But let's consider another function now. Let's consider that your function now looks like this. So your input is still x, then here you still have dy dx, right? But then your function looks like this. And for example, if you have 1 here, then you also have 1 here, but then if you have 2 here, then you have 0.25 here. That means that here in your dy dx, here it would equal 1/x squared. So now this is your function, and your goal now is to find the area under the curve starting from x equals 1 up until when x approaches infinity. Okay, so starting from here, you want to know what's the area under the curve as x approaches infinity. Well, my first intuition tells me that it should be infinity, because if x never ends, if this x never ends, then the area should never end either, right? So the area should also approach infinity. But is it true though? Let's find out. So let's calculate this integral and see what we will get. Dy equals 1/x squared dx. You can also write it down like this: x to the power of -2 dx. So we very simply put the integrals here and here and here, and then we go from 0 to x. Oh, my mistake, from 1 to x. Here we go from 1 to x, 1 to x. But then we should not forget that we have to put the limit here as x approaches infinity, and here as well, limit as x approaches infinity, and limit as x approaches infinity. So to calculate this integral, well, let's first of all take this integral like this. So x to the power of -2 times dx. Well, here in the denominator we put -2 plus 1, and then here we would have -2 plus 1, which means that we would have minus 1 times x to the power of minus 1, or minus 1 over x, right? And now we can say that y equals limit as x approaches infinity. So we would have minus 1 times 1 over x, and we're going to put it in the brackets. We should also initially put this minus 1 inside the brackets, but then you can factor it out. So let me show you what I mean. So instead of here, I'm going to put minus 1 here, right? I'm going to put minus 1 here. And then I'm going to go from 1 till x. Now, that would mean that I will have limit as x approaches infinity. So first of all, I would have minus 1 times 1 over x, and then I have minus, and then again the new function would be minus 1 divided by, and now I'm going to put this 1 inside here instead of x. Now if you see, then this constant can be now factored out. That's why when you have a constant, then you can just factor it out, put it here, and then you simply have 1 over x, and then minus 1, like this. But okay, if our x approaches infinity, then this becomes 0, right? And that means that your entire answer is 1. So there you go. If you go from 1 up until infinity, then your entire area under the curve is 1. So how can it be? It's not intuitive at all. Well, I can give you the intuition in two ways. The first way is if we look at this equation here that we get, right? So what do we have here? We have y equals, and then this entire thing, if we calculate like this, minus 1, and then you have 1 over x minus 1. You can also write it down like this. If you multiply everything by minus 1, then it would be 1 minus 1 over x. Okay? So that would be the function that you would get if you take this indefinite integral minus the constant, of course, because remember, with indefinite integrals you also need to put the constant. But here we're not dealing with indefinite integrals, but that would be one part of the indefinite integrals that we would get, right? And then we would simply put the initial and final values inside x. But then how would it look like graphically? Well, it would look like very simply like this. You have y here, and remember, now our area under the curve, right, now it's measured on this y number line, and your input stays the same. So if my input is 1, and I'm also going to put 2 here, and I'm also going to put 4 here. So if I look at this function, then if I have 1, if my x is 1, what will I get? Y equals 1 minus 1 over 1. Well, I get 0, right? So I'm here. Now if I have 2, then y equals 1 minus 1/2. I get 1/2, or 0.5, right? So I'm going to say that this is 0.5. There you go. Now if I have 4, if my x is 4, 1 minus 1/4. This is 0.25. So I will get 0.75, right? So I'm going to get it here, 0.75. So here's my point. And in fact, if my x approaches infinity, then this is 1 here, right? And as my x approaches infinity, then this term here becomes smaller and smaller. And if x approaches infinity, then this term disappears. It becomes 0. So therefore, my function would be something like this. It goes through these points, but then it will never ever grow bigger than 1. So it will always approach 1. You see, this is your theoretical limit here. And as your x approaches infinity, you get always closer to 1, but you never quite reach it. You can only get closer to it as your x approaches infinity. As your x gets bigger and bigger, you get closer to 1. And that is because this is your theoretical limit, and this term here becomes smaller and smaller as your x becomes bigger and bigger. And of course, this function would continue also below 1. When your x is smaller than 1, then your function would be here. But we only consider from 1 up until when x approaches infinity, right? So we start from here, and then we simply approach 1 like that all the time. And another way to look at it is like this. Let's consider a rectangle, right? And let's say that this rectangle, or the square, let's consider that the area of the square is 1, okay? And we don't care about the units right now. Well, we can say that, okay, this x is meters and y is meters. In that case, it would be 1 meter squared, okay? But you see, this square is empty. And this square is empty when x equals 1. You see, when x equals 1, your area is empty. Your area is 0. You see, your y is 0, but your y equals your area. So when x equals 1, your area is 0. Now, when your x equals 2, then my area is 0.5. So I cover half of the square, okay? So that is when my x equals 2. Now when my x equals 4, then my area is 0.75, which means I take the remaining empty rectangle and I cut it in half. So now this is when my x equals 4. You see, when my x equals 4, I have covered this area here and also this area here. So in total, if the total area of my square is 1, then once I have covered 4 x's starting from 1, okay, we start from 1. Once I have gone from x equals 1 to x equals 4, I have covered 0.75 meters squared, or 75% of my area in the square. And of course, if my x now equals 8, okay, when my x equals 8, then I will have covered 1/8 of the area. And then if my x equals 16, then it's like this. 32, it's like this, and I can go on and on and on, and you can see that I can always take the remaining empty area and I can cut it in half. And if I do that, I never quite reach area equals 1 meter squared, because I can always take the remaining empty area and cut it in half, right? So I can always cut it in half. So I will only be able to cover the entire rectangle when my x would be infinity, but it can't be infinity. So that means I will never be able to cover my entire rectangle, or in this case, my entire square. I will never be able to color it fully. I can only approach the square equals 1 meter squared, I can only approach this state as my x gets bigger and bigger and bigger. And so as my x approaches infinity, then I'm able to color my square more and more. But I'm never able to quite reach area equals 1 meter squared. Alright? So that's the intuition behind it. Okay, well, thank you very much for attending this lecture. And in the next lecture, I'm gonna show you how integrals are formulated mathematically in a formal way. See you then.
Welcome back. In this video, I want to show you a formal mathematical definition for definite integrals. And to do that, I'm just going to draw a random function here. And this is my input here, x. And this is my output, y. And let's say I have some kind of random function. And I want to calculate the area under the curve starting from A, and then I want to finish at B. So my A is x initial. So I'm gonna call it x initial, or x with an index of 0, and that will be my A. Alright? Now we already know how to calculate the area under the curve, or at least the logic of it. And so what we do, we divide this area into small rectangles, and then we just calculate these rectangles, the areas of these rectangles. And now the goal of this video is to first of all show you how to mathematically represent the calculation of these small areas here, and then how you would mathematically represent the addition of these areas, and then how you're gonna arrive to integrals when you do that. So let's continue. If this is x0, right? A is x0, then we're gonna say that the interval, right? The interval between these, or the width of these small rectangles, is delta x. Alright? And the width is the same for all of them. So if this is x0, then I'm going to say that this point here is x1. Then this point here is x2. And then I'm going to say that this point here, after whatever amount of rectangles, then this point here is x n minus 1. And then b is x with an index of n. Okay, so I have x0, x1, x2, then after some rectangles, x n minus 1, the penultimate point, and then I have x with the index of n here, which is b. Now, my goal here now is to find some kind of discrete function, right? Right now we're in the discrete world. Right now, I want to find a discrete function. I'm just going to put a df, a discrete function, right? Of which output is this discrete area under the curve, right? So in this case, it would look something like this, and then something like this, right? And here as well, something like this. So there will be a lot of rectangles here, and then if we sum them up, we will get our discrete area. So our goal is to find this discrete area, and our input here would be n, or the amount of intervals here, or the amount of these rectangles. Alright, so I need to find a function, a relationship that takes the amount of rectangles that I have, and then I have my discrete area. So I have to find this function here. So how would I do it? Well, first of all, how would we get this discrete area in the first place, knowing, for example, the interval or the width of one rectangle? Well, our discrete area could be written like this, that if I take my function y and then I put some kind of point inside, xi, it can be x1 or x2 or xn minus 1, it doesn't matter. If I do that, then what will this term give me? It will give me the height at that point. Let's say if I put here inside the y and then I put x2 inside the parenthesis, then what I will get this height here, right? So y at x2 gives me this height. Now, if I now multiply that height by delta x, then I will get this little area of this rectangle, right? I'm going to get the area of this rectangle. So if I put delta x here, then whatever x I put inside here, inside the parenthesis, then I would get the area of that rectangle. If I put xn minus 1 here, then I will get this rectangle here. If I put b inside here, or xn, then I will get this rectangle here, because y at xn will give me this height. If I multiply it by delta x, I will get the area. So in order to now sum all those rectangles up, right, because this formulation gives me the area of one rectangle depending on x sub I. So if I want to sum them all up, I just need to put the summation sign, and then I will have from I equals 1 up until n. Okay, so I start going from x1 gives me this height, and then times delta x, then I will get this area here, and then the next one would be x2, so I can even write it down here to make it more clear. So first y x sub 1 times delta x plus y at x2 times delta x plus, I'm just going to continue here, plus, then you would have y xn minus 1 times delta x, and plus y at xn or b times delta x, right? And this formulation gives me the total discrete area under the curve. So for example, this term here will give me this area here, all right? X n minus 1 times delta x, it goes to the left, and then that's how I will get my discrete area. But right now my discrete area is not as a function of n, it's as a function of delta x and then xi, right? So right now I have this kind of situation where I have delta x, and then I have some kind of xi, and then I have this function here, which is y at xi times delta x, and then I get my discrete area. Okay? But my goal was to find it as a function of n, as a function of the amount of rectangles that I have, which means that I have to take my two inputs that I have here, and I have to write them in terms of n, in terms of the amount of rectangles. Okay? So let's do that, and if we do that, then I can show you how you can get integrals out of it. So first of all, let's think about delta x. how could we write delta x as a function of the amount of rectangles? So now we are in this kind of situation where we have an input which is delta x, right? Now we need to find some kind of relationship so that we would have, in fact, now what we want to do, we want to have an input as the amount of rectangles, right? And then we will get delta x as an output. So now we want to find this kind of relationship. And how would we do it? Well, if you look at it, then if you look at B and A, right, what will you get if you subtract A from B? If you have this kind of expression, what will you get? B minus A. Well, you will get this distance, right? So this is at point A. I'm just going to write it down here. And this is B. You will get the distance from A to B, right? You will get how far B is from A. You will get this distance here. Okay? That's what you will get if you have B minus A. And now, what will happen if you divide this distance by the amount of rectangles? So by n. So if your n is 10, if you divide it by 10. So if I divide this by the amount of rectangles, what will I get? Well, I take this distance, right, from A to B, and if I divide it by n, I will chop it into small little pieces. And then the distance of that piece is delta x, right? And there you go. That's how you can write delta x as a function of n. Okay? So you just calculate the distance between A and B, and then you divide it by the amount of rectangles, and then you get your delta x. And now, so this function goes here, and now you can write your delta x as a function of n, which is what we wanted, because now we can put this expression here. Now let's go to the next one, x sub I. What would we do there? So again, we want n, and then n is our input, and then let's say now we want another function, and let's call it h, and then here we want x sub I. So we want n as an input, and some kind of impression should give us xi. Well, one way to do it is, let's just pick a random point. Let's just pick x2, right? So how would we get to x2? Well, I could write down an expression like this. I could say that, for example, x2, right, equals a plus 2 times delta x. Does it make sense? Yes. You're at point A, and then your x2, well, in order to get to x2 from A, you need to add 2 plus delta x. So you have 2 delta x's here. Delta x, and then another delta x. So you see, you can get it like this. Also, if, for example, if you want x1, then it would be a plus 1 times delta x, right? A plus 1 times delta x, and you're at x1. x0, a plus 0 times delta x, right? So this term will be 0, you're at a. xn minus 1, a plus, and then here you would have n minus 1 times delta x. And you're at this point. xn equals a plus n times delta x. And you're here. Okay? Now, this delta x, we already had the expression for delta x. So it was this expression. So in fact, this term here, this is like a counter, right? You count whether it's x1, x2, xn minus 1. This is the subindex, right? So we can say that the subindex, we can say that it's I, right? It's a counter. And then we can rewrite delta x like this. So we can say that xi equals, so this is the subindex I, a plus I times, and instead of delta x we put b minus a divided by n. You see? So this becomes I here. These terms, they become I. They are the subindices. And then instead of delta x you put this. You put this expression. And now you very simply take this function for our discrete area that I have rewritten here, right? And then you simply substitute delta x with this expression that we got earlier, with this expression, and you also substitute xi with this expression that we got earlier, this one here. And so this expression here is our discrete area, okay? Our discrete area. So we get all these small rectangles, and when we discretely sum them up, then we get an approximate area under the curve. But it's an approximate area with errors because we're doing it discretely. So now we have to go from discrete area to continuous area. And in order to do that, we have to take that n that we have here, right? And that n has to approach infinity. What will happen when n approaches infinity? What will happen? That means that the amount of rectangles increases more and more and more. So you will have more and more rectangles here, right? But at the same time, delta x becomes smaller and smaller and smaller. So if you look at this term, this is the delta x term, right? This is this. This is the delta x term. This term becomes smaller and smaller because n becomes bigger and bigger. The amount of rectangles increases, and so your interval b minus a, this distance stays the same, but if you have more rectangles, if the amount of rectangles is higher, then your delta x will be smaller. So this part here, this delta x, will go down, it becomes smaller. But at the same time you will have more, let's say, xi's, right? So if you look at this part here, then the amount of xi's, well, I just say that it's a number of xi's, the amount of xi's increases, right? So the logic is that the width of the rectangles goes down, but the amount of rectangles goes up, and then you will get closer and closer to the continuous world, so you will approximate the area under the curve better and better, right? And then when that happens, then your discrete summation becomes your continuous summation, which is an integral, right? And so this is the formal mathematical definition of a definite integral. The formal definition of a definite integral is obtained like this. So you take this discrete area here, the formula for the discrete area, and like we discussed before, if n approaches infinity, and now you take this entire formula and you take a limit of it as n approaches infinity. So what will happen? This term becomes smaller. Also, this term here becomes smaller, but then the amount of i's increases because your n gets bigger and bigger and bigger here. So now I goes from 1 up until a higher number. So if before it was 100, now it's maybe 1000. So now you will have 1000 summation terms. So this I becomes bigger, okay? So this becomes smaller here, delta x becomes smaller, but I becomes bigger, and then A remains the same, and B as well. And there you go. You take this entire formula that we have derived, and as n approaches infinity, then you go from discrete area to continuous area, and this is your definite integral. From a to b, your function, which is this, and your dx, which is this. And then if you take the integral of it, you get your exact area under the curve. And that's how a definite integral is formally defined. So now you know the formal definition of it. All right, thank you, and see you in the next lecture.